we'll try to record this. Okay, let's see if that works. Okay, so as I said, the Hohmann transfer orbit is follows Kepler's laws, and it is energetically efficient. Okay, so just going back to review Kepler's laws, we won't go into the ordeal that Kepler went through. You can play through those clips by Carl Sagan, who goes much more into the history of what Kepler had to go through to come up with these laws. But they're essentially three laws of planetary motions that Kepler came up with. First law is what?
Planets move in an ellipse around the sun.
Okay, planets don't go in circles, they go in an ellipse. The sun is at one focus of the ellipse. This is really drawn grossly not to scale, but one focus of the ellipse would be here, the other focus of the ellipse would be there. The sun occupies one of those foci, and it's the gravity of the sun that essentially flings the planet around in orbit. And so basically the planet is going to, if it's in an elliptical orbit, there's going to be a part of the orbit where it is going further and further and further away from the sun. Eventually the gravity of the sun pulls the planet back, and the other part of the ellipse, we have the planet becoming closer and closer and closer to the sun. Now these 2 points here, where the planet is closest to the sun and the planet is furthest away from the sun, they have their own names. Anybody recall that? Perihelion, meaning para means close, helion means the sun, Helios, sun god. Okay, so we have perihelion here, and the opposite of peri is api, far away, but aphelion sounds funny, so instead it's aphelion. Okay, so that's the first law, elliptical orbits. The planets can vary from almost circular. Okay, you can have an ellipse where the two foci are very close together, and the eccentricity, which is how squished, how oval-shaped that ellipse is small. Or you can have elliptical orbits that are much more stretched out. It really depends. In the case of Earth's orbit is fairly circular. And it has a low eccentricity. Mars is much higher eccentricity. Mars's orbit is much more elliptical looking than the Earth's, which looks fairly circular even though it's not quite a perfect circle. Okay, law number 2. It's got these funny pi sections here. If the planet is at its farthest away point from the sun, and the sun's gravity starts to pull it back on this part of the orbit where it's getting closer and closer to the sun, what's going to happen to the speed of the planet there? It will go faster, because basically gravity's drawing it in. So its lowest point would be at aphelion. I mean, imagine, I should have brought a visual aid. I should have brought my Mars globe, my Mars pillow. If you throw an object up away from Earth's gravity, it will eventually slow down until it starts going back the other direction. It's essentially what's happening here, except that instead of going straight up and then straight back down to the sun, which would not be very good, it's more of swinging around, getting up to the top of the arc, slowest, 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 and then begins falling back toward the sun, but because it's swinging around, it's not going to actually hit the sun. The sun's gravity will whip it around again, and this will be where it's going fastest, and then it will slow up again. So Kepler's second law is basically not only that, not only does the velocity slow down at aphelion and speed up at perihelion, but it does so in a precise mathematical relationship such that at any given time, elapsed time, this area here is going to be equal to this area here, which will be equal to the same as this area here, and so forth. So, yes, it's slower here, faster here, but it's in a specific relationship. And this law, it's kind of funny. Back when Kepler worked, the whole enterprise of science was about defining the laws of nature. And so you make a discovery back then, you get to call it, Kepler's law, first law, second law. Nobody talks about laws anymore. So if I discovered something really, really cool in an area of science, I really couldn't say Landa's law. Anyway, this allows very quantitative predictions about where planets will be, where any object will be that's following this kind of Keplerian orbit. And then the third one, first two I think are easy. Ellipses, fast versus slow. Third one's a little bit more obscure, but also very useful. We know that the further away from the sun a planet is, the longer its year, the longer it takes to go around the sun. But again, there is a precise mathematical relationship. And so if you take what's known as the semi-major axis of the ellipse, so essentially the maximum distance from this imaginary center of the ellipse. In the case of Earth, that would be 1 astronomical unit. In the case of Mars, it would be somewhere around 1.5 astronomical units. That is mathematically related to the period of time, the year of the planet, in the following way. If you take the period, square it, that's in years, that's going to be equal to this semi-major axis cubed in terms of astronomical units. So how many have got law number 3 down pat? Yeah. But essentially it's this right here. But just to kind of look at that third law again in a little bit more detail, we have A, oops. Here as a semi-major axis, and we have P is essentially how long it takes the planet to go around. So for the Earth, it's 150 million kilometers from the Earth to the Sun. For Mars, it's 227 million kilometers. And so as I said, the distance of Mars from the Sun is about 1.5, a little bit more than 1.5 astronomical units. So Mars is about 50% further out from the Sun than the Earth. And how long is a year on the Earth? 365 days. The orbital period for Mars in terms of days, not sols, is 687. Okay. So just to show you that this does work out, in this case, the distance from Earth to the Sun is 1.5 astronomical units. If you cube that, if you take 1.5 times 1.5 times 1.5, you get this value. And voila, if you take the square root of that, you get 1.88 years, Earth years, which is essentially how long the Martian year is in terms of Earth years. Okay? So, yay, Kepler was right. Now for going to Mars. Okay. When are Earth and Mars closest together? So if we have got the Sun here and the Earth there and Mars there, this is again known as opposition. Opposition is defined from the Earth as when the Sun and some planet are on opposite sides. That's why it's called opposition. So you can talk about when Mars is in opposition, you can talk about when Jupiter is at opposition, because there will be time during the year when, standing on the Earth, the Sun would be in one direction and Jupiter would be 180 degrees away. Can Venus ever be in opposition? Why not?
Because Venus is closer in.
Venus is closer in. So if Venus is going to line up, if there's going to be a line between the Earth and Venus and the Sun, it's either going to be because Venus is on this side of the orbit, and then Venus and the Sun will be in the same part of the sky. It's called conjunction. There is, for Venus, there would be an inferior conjunction when Venus is on the Earth side of the Sun, and there would be a superior conjunction when Venus is on the far side. Same thing with Mercury. Mercury cannot be in opposition. Mercury and Venus are always close to the Sun in the night sky. Okay. So if this is when Earth and Mars are closest, the simplest idea about sending a ship to Mars would be, let's wait till opposition, and then we'll just blast a ship straight over to Mars, and that'll be the closest distance. That should be the best way to send a craft to Mars, right? What's wrong with that? Why is that not the way to go to Mars?
Because by the time it got there, it wouldn't be in opposition.
Okay. So it'll still take a while for the craft to make it over that distance. Mars is moving, and so by the time the probe got here, Mars would already be long. But maybe you could act like you're a duck hunter or something and kind of lead Mars a little bit, right? That still will not work, because the rocket starting out at Earth has the same forward momentum that the Earth does. And so you're not really starting off with a stationary Earth and then aiming and shooting. So for a variety of reasons, this does not work. Instead, what you have to do is to send your craft along one of these elliptical orbits that all objects around the Sun follow. So in this case, we've got the orbit of the Earth here. And we've got the orbit of Mars here. And what we're doing with the spacecraft is putting it onto its own elliptical orbit where the perihelion, closest point to the Sun, is starting out on the Earth, and the aphelion is going to end up at Mars. So we're essentially taking the spacecraft and putting it on a different orbit than what it's starting out with on the Earth. It's going to take us energy to boost it into that orbit, and then it's going to take us energy to slow it down when it gets to Mars. But that is still the most effective, most efficient path for the spacecraft to take. And again, it follows those Kepler's laws. In elliptical orbit, the velocity is going to change predictably as it goes along that path, and the period of time it would take to complete a cycle is going to be dependent on that third law of Kepler's. Okay, so how does it all work? Rather than have you work through the math, I've just got it up here. We can just walk through the process. Essentially, in terms of the size of the orbit for the spacecraft, it's going to be an average between the size of the Earth's orbit and the size of Mars's orbit, right? Because it's going from this smaller distance out to this larger distance. And so basically all we have to do is add up and take the average of the semi-major axes for the Earth and Mars. And we come up with the average distance from the Sun for the probe is 1.26 astronomical units. Starts out at 1 astronomical unit, ends up at 1.5 astronomical units, 1.523, and so the average astronomical unit for the probe is 1.25. So with that, we can use Kepler's third law to figure out how long it would take the probe to make a loop from the Earth's orbit out to Mars and then back. That would be its year. It's one revolution around the Sun. And so essentially, in this case, I use t instead of p, but the orbital period, or the time squared, is divided by the distance cubed is equal to 1. Therefore, time squared equals distance cubed. You work this all out, and it is ends up being the square root of 2, which is 1.41 years to go for a round trip. So we started here, shot the probe off to Mars, but it didn't stop. It just came back around. It would take 1.4 Earth years to do that. So how long is it going to take to get to Mars? Half of that, right? Half of 1.4 is
0.7.
0.7. So it takes, for this minimum energy transfer, about 8.5 months for a probe to go from Earth to Mars. So the Maven mission and India's MOM mission blasted off several months ago. And they will be arriving later this fall at Mars. So Kepler's law gives us this 8.5 month journey. And finally, we want Mars to be at that point in its orbit when the probe gets there, right? Because it doesn't no good for the probe to get out to the orbit of Mars if Mars is over here somewhere. So we have to have the probe leave the Earth at a time when it and Mars will both arrive here at this point at the same time. So then it becomes a simple problem of the probe's going to be en route for 0.7 years. Mars's orbit is 1.88 years long. And so we need basically to launch from the Earth when Mars is 135 degrees away from that point where we want the rendezvous to take place. The upshot of this is that we can really only launch missions to Mars every 26 months. There's a launch window that opens up because it takes 26 months for the Earth and Mars to get into this kind of orientation. Then it's the best time to shoot off the rocket, and they will rendezvous here. And then we have to wait another 26 months before we can do it again. Questions? Had a question?
Would slingshotting around the moon be like an option to at least open the window of time in which we could?
Probably not slingshotting around the moon. I mean, this is the minimum energy trajectory. If we're willing to invest more energy, we can follow an orbital trajectory that is not quite this perfect Keplerian orbit between Earth orbit and Mars orbit. In particular, if we wanted to, we could pump excess energy, which would basically have the probe loop further around out, which means that it could actually intersect Mars, at a point earlier but it costs more energy to do that, and then it costs a lot of energy because you got to slow down to be captured into Mars orbit when you get there. Yes, we could do that if we weren't sending 2-ton rovers to Mars. Okay. As we'll see, it also varies a bit between different oppositions, because sometimes Mars is closer and further, other times it's further away. Because again, Mars's orbit is very eccentric. So, yeah, with enough energy, all things are possible. With enough energy, we could just basically point straight to Mars and fly our spacecraft like 1950s sci-fi movies with the direct reckoning. But not if we want to get the most payload there to Mars per capability of our launch vehicles.